There are 40 billion Earth-sized planets in the habitable zones of our galaxy. 40 billion places where liquid water could pool on the surface, where the temperature sits in that narrow band between freezing and boiling, where chemistry has every reason to turn into biology. That number comes from NASA's Kepler Space Telescope, which spent 9 years staring at roughly 150,000 stars, watching for the tiny dips in brightness caused by planets crossing in front of them. The statistical models built on that data estimate 40 billion potentially habitable worlds in the Milky Way alone, and the observable universe contains at least 2 trillion galaxies. Now hold that number in your mind. 40 billion possible homes for life, just in our galaxy, just around stars similar enough to our own to make the comparison meaningful. Spread those 40 billion planets across the Milky Way's disk, and one would sit within roughly every 2 light years of another. That is denser than the spacing between most stars. The real estate is not the problem. It has never been the problem. 65 years of organised searching, starting with a single radio telescope in West Virginia in 1960 and extending through some of the most powerful instruments humanity has ever constructed, has produced a single result. That result is zero. No confirmed extraterrestrial transmission, no verified alien signal, no evidence of engineering or technology or intelligence anywhere beyond Earth. Thousands of scientists across dozens of countries, hundreds of millions of dollars in funding, and the answer, as of early 2026, remains unchanged, zero. This is not a failure of effort. It is not a gap in the data or a problem of patience. Zero, at this scale and after this much time, is a measurement. It is arguably the most important measurement in the history of the search for extraterrestrial intelligence. And tonight, we are going to trace that measurement through 76 years of investigation. From a lunch table at a weapons laboratory in New Mexico to a signal that screamed across the hydrogen line for 72 seconds and never came back. From a telescope torn down to build a golf course, to an astronomer who broadcast humanity's location into the cosmos without asking a single person on Earth for permission. From a set of rocks on the ocean floor that shattered one of astrobiology's foundational assumptions to 2 papers published in the last 2 years that placed the Great Filter not behind us, but directly ahead. The silence out there is not empty. It is full of information, and the information, once you follow it far enough, becomes deeply unsettling. In March of 2020, after 21 years of continuous operation, a project called SETI at home quietly shut down. Most people never heard about it. The project had used millions of volunteer computers around the world to sift through radio telescope data, searching for patterns that might indicate an intelligent signal from somewhere beyond Earth. You could download a small program, and while you slept or worked, your computer would process tiny chunks of data recorded by radio telescopes. It was one of the largest distributed computing experiments ever attempted. Over 2 decades, those volunteer machines processed roughly 12 billion candidate signals. 12 billion. Every single one turned out to be noise. Interference from satellites, reflections from aircraft, electrical artifacts from nearby equipment, natural emissions from astrophysical objects doing what astrophysical objects do. Not one confirmed extraterrestrial transmission made it through the pipeline. The final result, after all that time and all that collective computing power, was zero. That number deserves more than a moment. It deserves the full weight of what it represents. Because SETI at home was only one thread in a much larger tapestry of searching, and every thread has ended the same way. The Breakthrough Listen program is the most comprehensive search for extraterrestrial intelligence ever mounted. Funded with $100 million from the Breakthrough Foundation, co-founded by the Russian-Israeli billionaire Yuri Milner. The project was announced in 2015 on a stage in London alongside Stephen Hawking. It gained access to some of the most powerful radio telescopes on the planet. The Green Bank Telescope in West Virginia, 100 meters in diameter, the largest fully steerable radio dish in the world. Parkes Telescope in Australia, 64 metres across, one of the most sensitive instruments in the Southern Hemisphere, Meerkat in South Africa, an array of 64 dishes designed for the next generation of radio astronomy, and the Automated Planet Finder at Lick Observatory in California, an optical telescope capable of detecting laser pulses from distant civilizations. By 2024, Breakthrough Listen had scanned approximately 1 million nearby stars. It had accumulated more than 2 petabytes of raw data, a volume that would fill roughly 400,000 DVDs. Its sensitivity was extraordinary. The instruments could detect a transmitter producing between 10 to the 12th and 10 to the 13th watts, roughly equivalent to the total power output of a small nuclear power plant, from nearby star systems within a few hundred light years. If anyone in our immediate cosmic neighbourhood was making any deliberate effort to be heard, these instruments would have caught it. They caught nothing. Then came an instrument called COSMIC, which stands for Commensal Open Source Multi-Mode Interferometer Cluster. It was installed on the Carl G. Jansky Very Large Array in New Mexico, that iconic collection of 27 radio dishes spread across the desert in a Y-shaped configuration. What made COSMIC different from previous SETI instruments was its operating model. It piggybacked on normal astronomical observations. Whatever the VLA was pointed at on any given night, COSMIC processed the same data in parallel, searching for narrowband signals that might indicate a technological source. It did not need its own telescope time. It watched everything the VLA watched and ran its own analysis on top. In its first 11 months of operation, from March 2023 through early 2024, COSMIC observed more than 950,000 unique fields. That paper was submitted for publication in the Astronomical Journal in early 2025 by Chenoa Tremblay and colleagues at the SETI Institute. The number of technosignatures detected across those 950,000 fields was 0. Meanwhile, in Western Australia, the Murchison Wide Field Array took a different approach entirely. Instead of searching individual stars, it surveyed 2,800 entire galaxies at radio wavelengths. The logic was straightforward. If a sufficiently advanced civilization had achieved galaxy-spanning engineering, it might produce signals detectable across intergalactic distances. Each of those 2,800 galaxies contained hundreds of billions of stars. The search covered a volume of space that dwarfed anything previously attempted. The result was the same: nothing. In October of 2024, the Allender Telescope Array, a field of 42 dishes in Northern California, designed specifically for SETI, conducted the longest continuous observation ever aimed at a single target. 28 hours pointed directly at the TRAPPIST-1, a red dwarf star 39 light years away that hosts 7 rocky planets, 3 of which sit in the habitable zone. That system is one of the most promising candidates for finding conditions suitable for life anywhere in our stellar neighbourhood. The search produced 2,264 candidate signals. Every single one was traced back to a source on Earth. Then in July of 2025, something entered the solar system from interstellar space, an object designated 3I/Atlas, only the 3rd confirmed interstellar visitor ever detected, following Oumuamua in 2017 and Borisov in 2019. The Allen Telescope Array pointed at it within days. Over 7.25 hours of observation, the array recorded 74 million narrowband hits. Automated filters reduced that number to 211 candidates worth a closer look. Breakthrough. Listen also observed the object with telescopes on 3 continents, including the Parkes Telescope and the Green Bank Telescope, the latter observing less than 24 hours before the object's closest approach to Earth in December 2025. Meerkat in South Africa searched for signals down to a power level equivalent to a mobile phone handset at the distance of the object. The final count of artificial signals detected from this interstellar visitor: 0. 74 million signals from the direction of an object that came from another star system and not one was anything other than terrestrial interference or natural noise. The searches are orders of magnitude larger than anything Frank Drake could have imagined when he pointed an 85-foot dish at two nearby stars in 1960. The instruments are more sensitive. The frequency coverage is broader. The analysis pipelines are faster, with artificial intelligence now accelerating Breakthrough Listen's data processing by a factor of 600, a result demonstrated in late 2025 using NVIDIA's Holoscan platform, deployed on the Allen Telescope Array. The tools have improved beyond recognition, and the number at the end of every pipeline remains the same number it was in 1960. 0. Now consider what we know about the places where life could exist. As of early 2026, astronomers have confirmed more than 6,000 exoplanets. That is not an estimate or a model. Those are worlds whose existence has been verified through repeated observation. The Kepler data pushed the fraction of stars with planets, that second variable in the Drake equation designated FP, from a guess of 0.2 in 1961 to effectively 1. Virtually every star in the Milky Way has at least one planet. Take the galaxy's estimated 200 to 400 billion stars and multiply by 1 instead of 0.2, and the number of planets jumps by a factor of 5 overnight. The habitable zone estimates followed. Roughly 40 billion Earth-sized planets orbiting within the zones around their stars where liquid water could persist on the surface. 40 billion potential laboratories where the chemistry of life could be running right now, and has been running in many cases for billions of years longer than it has been running on Earth. Every new exoplanet discovery tightened the paradox. Every upward revision of the habitable planet count made the silence more statistically significant, because the expected number kept climbing while the observed number stayed fixed. The gap between what the universe should contain and what we can actually detect grew wider with every improvement in our understanding of how common planets are. And then there is the question of life itself. Earth formed approximately 4.5 billion years ago from the gravitational accretion of dust and gas orbiting a young star. For the first several 100 million years, the surface was largely molten rock, bombarded by asteroids during a period geologists call the Late Heavy Bombardment. Conditions were, by any reasonable standard, terrible for the emergence of biology. Yet the last universal common ancestor of all life on Earth, the single organism from which every bacterium, every tree, every fish and every human descends, existed approximately 4.2 billion years ago. The gap between the planet cooling enough to sustain liquid water and the confirmed presence of life is somewhere between 300 and 400 million years, and much of that window was spent under conditions that should have been hostile to complex chemistry. Life did not wait for ideal conditions. It appeared almost as soon as conditions allowed, possibly sooner. If the origin of life, the technical term for which is abiogenesis, is that quick and that robust, then it should be happening on rocky planets throughout the galaxy right now, and has been happening for billions of years before now. Research published between 2023 and 2025 made this picture even more striking. Multiple independent studies demonstrated that amino acids, the chemical building blocks of proteins, and RNA nucleotides, the building blocks of genetic material, likely emerged together from the very beginning of prebiotic chemistry on Earth. They did not appear in sequence, one after the other. They appeared simultaneously, interacting in ways that made both components more stable and more functional than either would have been alone. The old model of the origin of life was like building a car, by first manufacturing a perfect engine, then adding wheels, then adding a frame. The new model says the engine and the wheels and the frame all emerge together, each piece making the others possible. Life was not one molecule getting lucky. It was a system of molecules bootstrapping itself into existence through cooperative chemistry. Every revision to the origin of life story over the past 3 years has made biology look easier to start, more chemically probable, more likely to occur wherever conditions permit it. And every one of those revisions has made the silence harder to explain, because if the path from chemistry to life is a highway, and the universe has had 13.6 billion years to travel it, the complete absence of traffic at the destination demands an explanation that chemistry alone cannot provide. Something is halting the journey after it begins. Something happens between the emergence of biology on a rocky planet and the emergence of a signal strong enough to cross interstellar distances. The universe had time, it had space, it had the raw materials. Every generation of stars produced heavier elements, seeding the next generation with more complex chemistry. And yet, across all of that time and all of those stars, the result we keep getting is the same: 0. To understand why that matters, and what it might mean for us specifically, you have to go back to a cafeteria in New Mexico, a summer afternoon in 1950, and a question asked over lunch that still, 76 years later, has no answer. The Los Alamos National Laboratory sits on a mesa in northern New Mexico, about 35 miles northwest of Santa Fe. In the summer of 1950, it was still one of the most secretive facilities on Earth. The scientists who worked there had built the atomic bomb less than a decade earlier, and many of the same minds were now working on what would come next. Among them was Enrico Fermi, one of the most accomplished physicists of the 20th century. Fermi had built the first nuclear reactor under the bleachers of a squash court at the University of Chicago. He had helped design the bombs dropped on Japan. He was known among his colleagues for his ability to make rough but remarkably accurate calculations about almost anything, a skill people called Fermi estimation. On a summer day in 1950, 4 physicists walked to lunch together: Fermi, Edward Teller, Herbert York, and Emil Konopinski. The conversation was light. Someone had mentioned a recent New Yorker cartoon about flying saucers. There had been a string of UFO reports in the news that summer, and the 4 men joked about them as they crossed the grounds toward the cafeteria. Teller, who would later become known as the father of the hydrogen bomb, made a quip about the probability of faster-than-light travel. The conversation drifted. Then partway through the meal, Fermi asked a question that stopped the table. "Where is everybody?" The other 3 understood immediately what he meant. Fermi was not asking about flying saucers or little green men. He was asking about mathematics. The Milky Way contains somewhere between 200 billion and 400 billion stars. It is roughly 13.6 billion years old. A technological civilization expanding at just 1% the speed of light, a pace far below anything requiring exotic physics, could cross the entire galaxy in 10 to 100 million years. That sounds like a long time until you compare it to the age of the galaxy itself. 100 million years is less than 1% of the Milky Way's lifespan. There has been enough time for a colonization wave to happen thousands of times over. Fermi did back-of-the-envelope calculations right there at the lunch table. The numbers were not close. They were not ambiguous. Even with conservative assumptions about how many stars have planets, how often life arises, and how long civilizations last, the galaxy should be crawling with evidence of intelligent activity, spacecraft, signals, engineering on a scale visible across interstellar distances. There should be something. There was nothing. The question landed differently from a normal scientific puzzle. Most problems in physics have a clear path to investigation. You build an instrument, you run an experiment, you collect data. But Fermi's question pointed at an absence, and absences are harder to study. You cannot point a telescope at silence and learn why it exists. The question sat unresolved for the rest of lunch. It sat unresolved for the rest of the decade. 25 years later, in 1975, Michael Hart formalized the argument in a paper published in the Quarterly Journal of the Royal Astronomical Society. Hart laid out the logic rigorously. If interstellar travel is possible even at very low speeds, and if civilizations arise with any regularity, the galaxy should already be colonized. The fact that it is not demands an explanation. Every proposed answer to that question now carries Fermi's name, even though he never wrote the argument down himself. He simply asked, and nobody could answer. To get a sense of the time scale involved, consider a compression. If you squeeze the entire history of the Milky Way into a single calendar year, with the galaxy's formation on January 1st and today on December 31st, 100 million years would be roughly 2.5 days. A colonization wave, moving at 1% of light speed, would cross the galaxy in a long weekend. The galaxy has had the equivalent of 365 days. The universe had time, it had space, it had the raw materials. Fermi expected someone at that lunch table to point out the flaw in the logic. Nobody did. For 10 years after that lunch, the question simply sat there. Nobody had the tools to look. Then one man decided to stop theorizing and start listening. On April 8th, 1960, a 29-year-old astronomer named Frank Drake pointed the 85-foot Tatel telescope at the National Radio Astronomy Observatory in Green Bank, West Virginia, toward two nearby sun-like stars, Tau Ceti and Epsilon Eridani. He tuned the receiver to 1,420 MHz. That frequency was not chosen at random. It is the emission frequency of neutral hydrogen, the most abundant element in the universe. The year before, in 1959, two physicists named Giuseppe Cocconi and Philip Morrison had published a paper in the journal Nature arguing that 1,420 MHz was the logical channel for interstellar communication. Any technological civilization would know about the hydrogen line. It was the universal frequency, the obvious place to listen if you wanted to hear someone talking across the stars. Drake called his effort Project Ozma, after the Queen of the Land of Oz. Over roughly 150 hours, spread across several months, he listened. At one point, a strong pulsing signal came through and the team froze. It turned out to be a high-altitude military aircraft. After that false alarm, the rest was silence. Ozma found nothing, but it proved that the search could be done systematically, and it established a method that every subsequent SETI experiment would follow. In November of 1961, Drake convened a small conference at Green Bank to formalise the search. 10 people attended, including a young Carl Sagan. Over the course of the meeting, they worked through what became known as the Drake equation. It was not really an equation in the mathematical sense. It was a framework for organising ignorance. You multiply the rate of star formation by the fraction of stars with planets, by the fraction of those planets that could support life, by the fraction where life actually develops, by the fraction where intelligence arises, by the fraction that build detectable technology, by the average lifespan of such civilizations. Each variable was a question mark. Multiply them all together, and you got an estimate of how many detectable civilizations might exist in the galaxy at any given time. The second variable in the equation, the fraction of stars with planets, was designated FP. Drake and his colleagues set it at 0.2, meaning 1 in 5 stars might have a planetary system. It was a guess. It felt generous at the time. Many astronomers in the early 1960s thought planetary formation might require unusual conditions. Solar systems like ours might be rare. Most stars might be bare. They were wrong by a factor of 5. Between 2009 and 2018, the Kepler Space Telescope stared at roughly 150,000 stars and confirmed 2,783 exoplanets through the transit method, watching for the tiny dips in starlight caused by a planet crossing in front of its host star. The statistical analysis that followed upended the field. Virtually every star in the Milky Way has at least one planet. The fraction FP went from 0.2 to effectively 1.0. Every star. The number of planets in the galaxy jumped by a factor of 5 overnight, but the impact went beyond simple counting. Kepler revealed an astonishing diversity of planetary systems that nobody had predicted. Planets larger than Earth but smaller than Neptune, a class called super-Earths and mini-Neptunes, turned out to be the most common type of planet in the galaxy. They have no counterpart in our own solar system. Some planets orbit their stars in a matter of hours, so close that their surfaces are oceans of molten rock, and others circle in pairs, locked in orbital resonances where the gravitational pull of each planet influences the other's path. There are planets orbiting binary star systems, worlds with two suns in their sky. There are rogue planets drifting through interstellar space with no star at all, ejected from their birth systems by gravitational interactions and wandering the galaxy in permanent darkness. The number of these starless wanderers may exceed the number of stars in the galaxy by a factor of several. After Kepler's primary mission ended when a reaction wheel failed in 2013, the telescope was repurposed as the K2 mission, continuing to find planets until it ran out of fuel in 2018. Its successor, the Transiting Exoplanet Survey satellite, known as TSS, launched in 2018 and has been scanning the entire sky ever since, focusing on the brightest and nearest stars. TESS is optimized for finding planets around stars close enough that follow-up observations, including atmospheric analysis by the James Webb Space Telescope, are feasible. As of 2026, the total count of confirmed exoplanets from all surveys combined exceeds 6,000, with thousands more candidates awaiting verification. The cumulative effect of these discoveries was to transform the question at the heart of the Fermi paradox. Before Kepler, it was possible to argue that planets were rare, that solar systems like ours were unusual, that the conditions for life might exist in only a tiny fraction of stellar neighbourhoods. After Kepler, that argument was gone. Planets are not rare. They are the default state of stellar evolution. Almost every star you see in the night sky has at least one world orbiting it, and many have several. This was supposed to be good news. More planets means more chances for life, more chances for civilizations, more chances for contact. Instead, it made the silence catastrophically worse, because if the real estate was always this abundant, the question was no longer whether there were enough planets. The question became, with 40 billion potential homes, why is nobody there? 7 years after Project Ozma, a graduate student accidentally found something that everyone initially mistook for the answer. In 1967, Jocelyn Bell Burnell, working at the Mullard Radio Astronomy Observatory at Cambridge, was analysing data from a radio telescope designed to study quasars. She noticed a signal, a rapid, precise pulse repeating every 1.337 seconds. Nothing in nature was known to pulse with that kind of regularity. The research team labelled the source LGM1, Little Green Men. They were half joking, but only half. For weeks, the possibility of an artificial origin sat on the table. Bell Burnell and her supervisor Anthony Hewish considered it seriously. Then a second pulsing source was found in a completely different part of the sky, and then a third. The explanation turned out to be rotating neutron stars, collapsed stellar cores, remnants of massive stars that had exploded as supernovae, spinning at extraordinary speeds and sweeping beams of radio energy outward like a cosmic lighthouse. The signals were natural. They were named pulsars. The discovery earned Hewish a Nobel Prize, though Bell Burnell, who actually found the first signal, was controversially excluded from the award. The episode mattered for a reason beyond the discovery itself. It demonstrated that the universe produces phenomena that mimic intelligence with uncomfortable precision. A perfectly timed pulse repeating without variation looks designed. It was not. Nature can be deceptively regular, and that lesson would become relevant again and again over the following decades, because the history of SETI is, in many ways, a history of false pattern recognition. The universe keeps generating signals that look like someone is trying to communicate, and every time the explanation turns out to be physics doing something nobody predicted. 10 years after LGM1, the opposite happened. On August 15th, 1977, a volunteer astronomer named Jerry E. Mann was reviewing data printouts from the Big Ear radio telescope at Ohio State University. Big Ear was a flat reflector telescope that scanned strips of sky as the Earth rotated. The data came out on continuous paper, columns of alphanumeric characters representing signal intensity at different frequencies. One sequence jumped off the page. At exactly 1420.726 MHz, the hydrogen line, a signal appeared that was roughly 30 times louder than the background noise of deep space. The signal lasted 72 seconds, which was exactly how long a celestial source would remain in Big Ear's beam as the Earth turned. It behaved precisely the way an extraterrestrial transmission should behave. It was on the right frequency, it was the right duration, it was far too strong to be explained by any ordinary astrophysical source at that wavelength. Eman circled the character sequence on the printout and wrote a single word in red ink in the margin. Wow! The signal never repeated. Eamon and others pointed Big Ear at the same patch of sky hundreds of times over the following years. Nothing. Other telescopes searched the same coordinates. Nothing. The signal came from the direction of the constellation Sagittarius, from a region of sky with no remarkable star or known object. For the next 40 years, the WOW signal sat as the single strongest candidate for an extraterrestrial transmission in the entire history of the search. One burst, 72 seconds, then silence. In 2017, an astronomer named Antonio Paris proposed an explanation that seemed to close the case. 2 comets had been in the general area of Big Ear's beam on the night of August 15th, 1977. Paris argued that hydrogen clouds surrounding these comets could produce emission at 1420 MHz, mimicking the signal. Several news outlets reported the mystery as solved. The explanation was clean, comfortable, and allowed the scientific community to move on. Except there were problems from the start. Other astronomers pointed out that the comets were not actually in the correct beam position. Big Ear had 2 feed horns, and the geometry did not place either comet in the right one. More fundamentally, comets emit radio signals at 1420 MHz at extremely low power, measured in millijanskis. The WOW signal exceeded 250 janskis. The difference between what a comet can produce and what was actually detected spans many orders of magnitude. It is like proposing that a birthday candle caused a wildfire visible from orbit. The scale was simply wrong. The debunking of the comet hypothesis happened gradually. Multiple researchers published critiques between 2017 and 2018, but the debunking never received the same attention as the original claim. In popular culture, the comet explanation stuck. It was simple. It let people stop wondering. Then a team decided to go back to the raw data. In 2024 and 2025, researchers led by Abel Mendez at the University of Puerto Rico at Arecibo conducted the first comprehensive reanalysis of the original Big Ear data in decades. They used optical character recognition to digitize more than 75,000 pages of the telescope's archival dot matrix printouts from the 1970s. Nobody had ever conducted a full systematic review of this volume of material since the signal was first detected. The results confirmed what Eman had seen, but with greater precision. The WOW signal's flux density exceeded 250 janskis. At that power level, the comet explanation collapses completely. The positional analysis confirmed what critics had argued for years. Neither comet was in the correct feed horn beam on that date. The frequency was revised to 1420.726 MHz, and the researchers found no evidence that the signal was caused by terrestrial radio interference. So if it was not a comet, and it was not interference, and it was not a satellite, what was it? The new best explanation is stranger than any of those, and stranger than aliens. Mendez and his team proposed that the WOW signal was a rare superradiance event, a type of hydrogen mesa flare, possibly triggered by a magnetar. In specific and unusual conditions, a cloud of cold hydrogen gas in interstellar space can be stimulated to emit a sudden, intense burst of radiation at exactly 1420 megahertz. If a magneta, a neutron star with an extremely powerful magnetic field, passes near or through such a cloud, it can trigger this kind of coherent emission. The result is a one-time cosmic burst of perfectly tuned radiation, brief, non-repeating, and extraordinarily powerful. This explanation fits every observed characteristic. The frequency is exactly right because the emission comes from the hydrogen itself. The intensity is consistent with superradiance amplification. The 72-second duration matches the beam transit time, and the non-repeating nature makes sense because superradiance events depend on a specific alignment of conditions that may never recur in the same location. Imagine a balloon filled with gas that has been slowly pressurized for thousands of years. One day a spark hits it. The balloon does not deflate slowly. It releases all its energy in a single flash. Then it is gone. The conditions that built it up no longer exist. You could watch that spot in the sky for another 50 years and never see it happen again. The wow signal was not intelligence. It was not comets. It was something the universe produced naturally, but so rarely that nobody had predicted it. The cosmos generated a signal that perfectly mimicked what we expected from an alien civilization at exactly the frequency we were listening on through raw physics. And the telescope that caught it, the Big Ear radio telescope, operated from 1963 until it was demolished sometime between 1997 and 1998. The land in Delaware, Ohio was sold to a developer. The developer built a golf course. The instrument that captured humanity's most compelling candidate for an alien signal was torn down so that people could play 18 holes on the ground where it once listened to the sky. If you visit that location today, there is nothing to indicate what once stood there. This pattern, where the universe generates a perfect false positive and the instrument that detected it is destroyed, would repeat in different forms for the next 4 decades, and every repetition made the central question harder and more urgent. If nature keeps producing signals that look exactly like intelligence, how would we recognize the real thing if it ever appeared? The answer, increasingly, is that we might not. And that realization pushed scientists toward a different kind of question entirely. Not where are the signals, but what is preventing civilizations from existing long enough to produce them? In 1996, a man who was not an astronomer and not a physicist looked at this exact problem and gave the bottleneck a name. Robin Hanson was an economist at George Mason University. Economics might seem like a strange discipline to bring to a question about extraterrestrial intelligence, but Hanson's approach was built on something economists understand better than anyone else: probability under uncertainty, betting the odds, the logic of what a rational market would conclude from the available evidence. His reasoning went like this: between a dead rock and a galaxy-spanning civilization, there is a long chain of necessary steps, forming a planet with the right conditions, developing simple life, evolving complex cells, producing multicellular organisms, developing intelligence, building technology, surviving long enough to expand beyond a single world. If the galaxy should be full of civilizations but is not, then at least one of those steps must be extraordinarily difficult. A bottleneck so severe that almost nobody gets through it, not 1 in 1,000, not 1 in 1,000,000. A bottleneck with a near-zero pass rate. Hanson called it the Great Filter. The concept does not require you to know which step is the hard one. You just have to accept that the silence proves a filter exists somewhere in the chain. The math demands it. If every step were reasonably probable, the galaxy would be visibly colonized. It is not. Therefore, at least one step has a probability close to 0. The critical question is not whether the Great Filter exists. The silence already answers that. The critical question is where it sits. And this is where the concept stops being abstract and becomes personal. If the Great Filter is behind us, somewhere in the early steps, then we already passed it. Maybe the origin of life is the hard part, and we got lucky. Maybe the jump from single-celled organisms to complex multicellular life is nearly impossible, and Earth just happened to clear that hurdle. Maybe developing technology-capable intelligence requires a chain of geological and evolutionary coincidences so specific that it has only occurred once in 13.6 billion years. If the filter is behind us, we are rare, but we are safe. The hard part is over. If the great filter is ahead of us, somewhere in the later steps, then every civilization that reaches our level of technology eventually hits a wall it cannot survive. Nuclear war, environmental collapse, engineered pandemics, artificial intelligence that escapes human control, something we have not imagined yet. Under this scenario, the silence is not just absence, it is a graveyard. Every civilization that got as far as we have either destroyed itself, faded away, or went quiet before anyone in the neighbourhood had a chance to notice. For years after Hansen published his paper, the optimists had the stronger case. The emergence of complex life does appear to be genuinely difficult on Earth's own timeline. The planet spent roughly 2 billion years stuck at the single-celled stage before the jump to multicellular organisms. Intelligence took another 2 billion years after that. These are enormous stretches of time, and the probability of success at each transition might be extremely low. It seemed plausible, even likely, that we had already cleared the hardest steps. To make the stakes concrete, imagine 100 civilizations starting the journey from simple chemistry to interstellar communication. If the filter is behind us, 99 of them never get past microbial life, and we are the one that did. Dangerous but done. If the filter is ahead of us, all 100 develop technology, and 99 are destroyed before they can leave their home planet. We have built the rockets. We have built the radio telescopes. We have not yet crossed whatever line kills the others. For 2 decades after Hansen's paper, the debate stayed roughly balanced. Good arguments on both sides. No decisive evidence either way. Then, in 2024, a paper landed that shifted the weight sharply toward the worst-case scenario. Michael Garrett is an astrophysicist at the University of Manchester and the director of the Jodrell Bank Centre for Astrophysics. In 2024, he published a paper in the journal Acta Astronautica proposing that artificial intelligence is the great filter. His argument was built on a timeline that is difficult to argue with because we are living inside it. Earth's first radio transmission occurred in 1895, and when Guglielmo Marconi sent signals across a distance of about 1.25 miles. 127 years later, in 2022, generative artificial intelligence systems began operating at a level that surprised even their creators. The jump from first radio wave to sophisticated AI took just over a century. Garrett's model assumes that any technological civilization follows a similar trajectory, because the underlying pressures are the same. Once you develop electronics, the path toward increasingly autonomous computing systems is not optional. It is driven by economic competition, military advantage, and the basic logic of tool improvement. Every civilization that develops radio will develop computers. Every civilization that develops computers will develop artificial intelligence. The sequence is not a choice. It is a consequence. Garrett's estimate for the window between developing artificial intelligence and being destroyed or fundamentally altered by it is roughly 200 years. Not thousands, not millions, 2 centuries. That is the total duration during which a civilization might be broadcasting detectable signals while still existing in a form that would produce those signals. Apply that window to the galaxy. The Milky Way is 13.6 billion years old. A civilization's detectable phase lasts 200 years. That ratio is like trying to photograph a specific lightning bolt during a thunderstorm that lasts 4 million years. Even if millions of civilizations have arisen across the galaxy's history, the probability that any 2 of them overlap in their 200-year detectable windows is vanishingly small. The model does not require artificial intelligence to physically destroy a civilization in a dramatic cinematic fashion. It also accounts for quieter scenarios. a species that merges with its machines, a species that is gradually replaced by autonomous systems that have no interest in radio communication, a species that simply stops broadcasting because its AI-driven infrastructure has no need for the kind of omnidirectional electromagnetic leakage that makes a planet detectable across interstellar distances. Under any of these outcomes, the observable signature vanishes. The civilization goes dark. From the outside, it looks exactly like extinction, even if the underlying reality is transformation. Look at Earth's own trajectory for evidence that this is already happening. Military radar, the loudest signal humanity produces, operates at roughly 10 to the 14th watts in directional bursts. Those signals are detectable by a Green Bank-class telescope, 100 meters across, from about 200 light-years away. That sounds like a significant reach until you consider that 200 light-years covers roughly 15,000 stars. The Milky Way contains between 200 billion and 400 billion stars. Our loudest screams reach less than 1/10,000th of 1% of the galaxy. And we are getting quieter every year. Fiber optic cables carry data through glass, not through the air. Cellular networks use low-power transmitters aimed at the ground, not at the sky. Digital signals are compressed and encrypted in ways that make them indistinguishable from random noise to a distant receiver. Military radar systems are shifting to phased arrays that focus energy in the tight, directional beams rather than broadcasting it in every direction. Earth in 1970 was a bonfire visible from miles away. Earth in 2026 is a flashlight pointed at the floor. We are closing our own detectable window from the inside, and we are doing it for reasons that have nothing to do with SETI or alien civilizations. We are doing it because efficiency demands it. But the AI filter was not the only mechanism proposed to explain how civilizations might fail after reaching technological maturity. There is another path to extinction that requires no machines, no wars, no external catastrophe at all. It requires only one thing: a species smart enough to separate reproduction from survival. Birth rates are falling across the developed world, not as a temporary fluctuation, but as a sustained, accelerating trend that no government has managed to reverse. The data is not ambiguous. South Korea's total fertility rate hit 0.72 in 2023, the lowest ever recorded by any country. That means for every 2 adults, fewer than 1 child was being born. Replacement level, the rate needed to maintain a stable population without immigration, is 2.1. South Korea was not at a half replacement, it was at roughly 1/3. In 2024, the rate rose marginally to 0.75, which broke a 9-year decline, but remained far below any level compatible with long-term population stability. The country has spent more than $270 billion over 16 years on pronatalist incentives, cash bonuses for newborns, housing support for young families, tax cuts for married couples. The effect has been negligible. Japan's fertility rate sits at approximately 1.2, Italy at 1.24. China dropped below replacement in 2022 and is accelerating downward. The United States fell below replacement in 2021. These are not projections or estimates. These are census numbers, measured and published by national statistics agencies. The pattern is global. Every nation that industrializes, that educates its population, that gives its citizens reproductive choice, sees the same curve. Fertility drops. It drops below replacement. And once it drops far enough, the mathematics of population decline becomes self-reinforcing. Fewer young people means fewer potential parents in the next generation. The base of the population pyramid narrows with each cycle. Economic systems built on growth begin to contract. The infrastructure needed to support an aging population becomes unbearable for a shrinking workforce. Every government that has tried to reverse this trend has failed. Pronatalist policies in Scandinavia, in Japan, in Singapore, in Hungary, have all produced temporary bumps of a few percentage points before the decline resumed. France, which has the most generous family support system in Europe, including extensive parental leave, childcare subsidies and direct financial support for families, still fell below replacement. The argument that this pattern might be universal, that any intelligent species that gains control over its own reproduction will follow a similar curve, has been discussed in the demographic and astrobiological literature. The logic is thermodynamic in character. In a subsistence society, children are labour. They work the fields, tend the animals, care for aging parents. The economic incentive to reproduce is built into the structure of survival itself. In a technological society, children are cost. They require education, housing, time, attention, and resources that could be directed elsewhere. The calculus flips once individuals have the ability to choose whether to reproduce, and once the economic and social pressures that once made reproduction necessary are removed. Fertility declines, not because people are unhappy, not because society has failed, but because the incentive structure that drove reproduction for millions of years has been quietly dismantled by prosperity itself. If this is universal, if every intelligent species that gains control over its own fertility follows the same downward curve, it would explain the silence without invoking any catastrophe at all. No nuclear war, no asteroid impact, no artificial intelligence uprising, just a slow, quiet fade across every inhabited world in every galaxy. Civilizations rise, they develop technology, they decouple reproduction from survival. Their populations peak, stabilize briefly, and then decline across a few hundred generations until the infrastructure needed to sustain a technological society can no longer be maintained. The galaxy, under this model, fills with ruins rather than conquerors. Empty cities on worlds where the lights went out not with a bang, but with the soft click of a maternity ward that simply stopped receiving patients. Two proposed filters then. Garrett's artificial intelligence window of roughly 200 years, and a demographic decline curve of perhaps 500 to 1,000 years. These are not mutually exclusive. A civilization could face both simultaneously, and both are already measurable in human data, in trends that are happening right now, in numbers published by government agencies and academic journals this year. For decades, the optimistic view held that the Great Filter was behind us. The hard step was the origin of life, or the jump to multicellular complexity, or the emergence of intelligence itself. We had already cleared those hurdles. We were through the worst of it. The recent evidence says otherwise. The filter may be ahead of us, and we may already be inside the danger zone. But both of these filters assume civilizations either destroy themselves or fade away. And before we get to the alternative, there is a deeper geological argument that needs to be followed to its end. Because for 15 years it was the standard explanation for why we might be alone, and recent science has complicated it in ways that make the whole picture messier and harder to resolve. In the year 2000, two scientists at the University of Washington, Peter Ward and Donald Brownlee, published a book called Rare Earth. It became one of the most influential arguments in the history of the Fermi paradox. Their case rested on a chain of requirements that seemed both logical and supported by what was known about Earth's geological history. Complex life, the kind that builds civilizations, needs a stable climate over billions of years. A stable climate needs plate tectonics to regulate carbon dioxide levels in the atmosphere, recycle nutrients from the ocean floor back into the biosphere, and help maintain a planetary magnetic field strong enough to protect the surface from solar radiation. Plate tectonics in turn requires a very specific internal heat budget and a mantle of the right composition. Earth has all of these things. Most planets, Ward and Brownlee argued, probably do not. The logic was elegant. We are rare because our geology is rare. Intelligence did not just require the right chemistry and the right biology. It required the right kind of planet with the right internal dynamics, maintained over the right timescales. And those conditions might be so uncommon that Earth, is essentially a geological freak, a 1 in a billion configuration that just happened to produce the right environment for complexity to build on itself for 4.5 billion years without interruption. For a decade and a half, the rare earth hypothesis was the standard explanation for the silence. It fit neatly with the Fermi paradox. If plate tectonics are an unlikely geological accident, and if intelligence requires plate tectonics, then the Great Filter is geological, and we have already passed it. We are on the lucky side. The hard part is done. The silence makes sense because nobody else won the planetary lottery. Then the models started to disagree. Computer simulations conducted between 2015 and 2024 gradually undermined the neat causal chain that Ward and Brownlee had proposed. Some models showed that plate tectonics on Earth might not have preceded the emergence of complex life in the way the rare Earth hypothesis required. Instead, tectonics may have arisen partly because of complex life itself. Biological activity on the surface, particularly the chemical weathering of rocks by organisms, may have weakened the crust enough to allow subduction, the process where one tectonic plate slides beneath another to begin in the first place. If this is correct, the causal relationship runs in the opposite direction from what rare earth assumed. Life does not need tectonics. Tectonics may need life. Other simulations produced a different complication entirely. Some models demonstrated that plate tectonics can actually slow the oxygenation of the atmosphere rather than accelerate it. The subduction process pulls oxidized material, rock that has already reacted with oxygen, back down into the mantle, effectively removing it from the surface environment. If the geological process that was supposed to be necessary for complex life is actually delaying the atmospheric conditions that complex life requires, the rare earth framework loses one of its load-bearing walls. And then there was Pluto. When NASA's New Horizons spacecraft flew past the Pluto system in July of 2015, it sent back images that nobody had expected. Pluto's surface showed evidence of geological activity that defied every prediction. There were fractured ice plates. There was evidence of convective overturn in a vast nitrogen ice glacier called Sputnik Planitia, a region spanning roughly 620 miles across, larger than the state of Texas. Charon, Pluto's largest moon, showed similar signs of past geological activity. These are worlds billions of miles from the nearest warmth. Pluto receives about 1,000th the solar energy that Earth gets. Nobody had predicted active geology there. The discovery did not prove that plate tectonics are common throughout the universe, but it demonstrated that geological activity can arise in conditions far outside the narrow window that the rare earth hypothesis had proposed. If ice worlds at the edge of the solar system can exhibit geological complexity, the requirements for geology might not be nearly as restrictive as Ward and Brownlee assumed. None of this disproves the idea that intelligence requires specific geological conditions. What it does is complicate the story. The clean narrative, where a rare type of tectonic activity on a rare type of planet produces a rare type of biosphere that eventually generates a rare type of intelligence, keeps getting messier with each new model and each new observation. The requirements for intelligence might still be steep, but they might not be the requirements that were listed. There is another geological dimension to this that is rarely discussed, but may be equally important. Earth has a large moon. Our moon is unusually massive relative to its planet. It stabilizes Earth's axial tilt, which keeps the seasons moderate, and the climate relatively predictable over long time scales. Without the moon, Earth's axis would wobble chaotically, potentially causing extreme climate swings that would make the kind of long-term environmental stability needed for complex evolution very difficult to maintain. The moon is thought to have formed from a giant impact early in Earth's history, when a Mars-sized body struck the young planet and blasted debris into orbit that eventually coalesced into our satellite. That impact was a specific event that happened to occur at a specific time with a specific geometry. If it had not happened, or had happened differently, Earth might not have had the climate stability needed to support billions of years of biological evolution. How many of the 40 billion potentially habitable planets in the galaxy also have large stabilizing moons formed by similar chance impacts? We do not know, but the number is almost certainly less than 40 billion, possibly much less. The geology argument, even in its weakened form, still carries weight. It simply carries it differently than it did in 2000. The Great Filter may not be plate tectonics specifically. It may be a combination of geological, orbital, and chemical factors that collectively produce a planetary environment capable of sustaining the kind of long-duration stability that intelligence requires. And if those factors are rare enough, even the combination of easier biogenesis and abundant real estate might not produce very many civilizations. This is where the investigation hits a wall that cannot be resolved with current instruments. We know that life starts easily. We know that planets are everywhere. We know that habitable zones are common, but we do not know how common the full package is. The planet with the right tectonics, the right moon, the right magnetic field, the right ratio of ocean to continent, the right distance from galactic hazards, maintained for the right duration. Each of those requirements is an additional filter, and the combined probability could be vanishingly small even if any individual factor is not particularly restrictive. The mathematics of compound probability are not intuitive. If 10 independent conditions each have a 1 in 10 chance of being met, the probability of all 10 being met simultaneously is not 1 in 10. It is 1 in 10 billion. Stack enough moderately unlikely conditions together, and the combined probability drops to a level that looks impossible, even when every individual step looked achievable. This is the same mathematical principle that makes winning the lottery so unlikely. Each individual number is not hard to match. Matching all of them at once is nearly impossible, and the chain of conditions required for a technological civilization may have far more links than 10. Consider just a partial list. You need a rocky planet of the right size, not so small that it loses its atmosphere and not so large that it becomes a gas dwarf. You need it at the right distance from its star for liquid water. You need the star itself to be stable over billions of years, not a variable star that periodically sterilizes its planets with radiation flares. You need a planetary magnetic field strong enough to deflect the stellar wind that would otherwise strip the atmosphere. You need enough water to create oceans, but not so much that the entire surface is drowned, with no land for complex terrestrial ecosystems. You need a source of tectonic recycling to regulate the atmosphere's composition over geological time. You need a large moon or some equivalent mechanism to stabilize the planet's axial tilt. You need the planet to avoid being struck by a large enough asteroid to sterilize the surface during the critical period when complex life is developing. You need the star to be in a relatively quiet region of the galaxy, not near the galactic center where radiation levels are extreme, and not in a region subject to frequent nearby supernovae. You need billions of years of uninterrupted stability for all of these conditions to persist simultaneously. Each of those conditions may be common, many of them probably are, but the joint probability of all of them occurring together on a single planet may be small enough to explain why, in a galaxy of 40 billion potentially habitable worlds, the number that actually produce detectable civilizations rounds to zero. This is the core tension of the Fermi paradox in its modern form. The optimistic variables, the ones we can measure, keep getting more optimistic, but the silence has not changed, which means the pessimistic variables, the ones we cannot yet measure, must be doing an enormous amount of work to counterbalance the optimism. Something in the chain is harder than it looks, and the fact that we cannot identify it with certainty is part of what makes the silence so unsettling. Because there is a version of the story where the hard step is the one we are living through right now, the step between developing technology and surviving what that technology makes possible. If that is where the filter sits, the silence is not a mystery, it is a warning. But both of these filters, the geological rarity argument and the self-destruction argument, Assume civilizations either destroy themselves or fade away. There is another possibility, one that receives less attention because it does not involve death or decline at all. What if civilizations do not fail? What if they just go quiet? Here is a fact that undermines one of the central assumptions of the entire search for extraterrestrial intelligence. Earth is getting quieter, not louder. Quieter. In the 1960s and 1970s, humanity was loud. Omnidirectional radio broadcasts, television signals, and military radar systems pumped electromagnetic radiation into space in every direction. The signals radiated outward at the speed of light, forming an expanding bubble of detectable noise around our planet. Military radar, the most powerful source, peaks at roughly 10 to the 14th watts when measured directionally. A telescope the size of the Green Bank dish, 100 meters across, could detect those signals from about 200 light-years away. 200 light-years sounds like an impressive distance. It is not. 200 light-years covers roughly 15,000 stars. The Milky Way contains somewhere between 200 billion and 400 billion. Our loudest transmissions reach roughly 4/10,000ths of 1% of the galaxy. We are invisible to everything else, and we are becoming more invisible with each passing year. Fiber optic cables carry data through glass strands at the speed of light, generating no radio emissions whatsoever. Cellular networks use low-power transmitters aimed at receivers on the ground, not at the sky. Digital signals are compressed and encrypted, which makes them look indistinguishable from random noise to any receiver not specifically configured to decode them. Military radar is transitioning from omnidirectional dishes to phased array systems that focus energy in tight, narrow beams aimed at specific targets rather than spraying it across the horizon. Seth Shostak at the SETI Institute has been making this point for years. Advanced civilizations are not louder than primitive ones, they are quieter. A civilization 1,000 years ahead of us might communicate entirely through tight beam lasers, quantum encrypted channels, or technologies that have not been invented yet by anyone on Earth. Their communications would be invisible to us, for the same reason that a letter delivered by mail is invisible to someone standing on a street corner listening for a town crier's shout. The information flow increased by orders of magnitude. The noise dropped to nothing. A civilization using tight beam communication could be exchanging more data in 1 second than humanity has broadcast in its entire radio history, and we would never detect a trace of it. An alien civilization monitoring Earth from 500 light-years away in 1970 would have picked up our television signals. The same civilization monitoring Earth in 2070 might detect nothing at all. We would look dead, not because we had ceased to exist, but because we had upgraded our infrastructure. This applies in reverse. A civilization 500 light-years away that went through the same technological transition 500 years ago would already be invisible to us. We would point our telescopes at their star and hear silence, not because they failed, not because they destroyed themselves, because they became efficient. The entire logic of SETI, listening for electromagnetic leakage, depends on catching civilizations during a narrow window when they are technologically advanced enough to broadcast but not yet efficient enough to stop leaking. That window might be 100 years, maybe 200. On a cosmic timeline of 13.6 billion years, 200 years is nothing. It is a camera shutter, click. So perhaps the silence is not evidence of extinction at all. Perhaps it is evidence of graduation. But if that explanation was supposed to be comforting, the next chapter of the investigation takes that comfort away. Because some scientists were not content to just listen for leakage. They wanted to look for something bigger, something physical, something you could see across the entire galaxy if it existed. In 2024, a project called Hephaestus published results that made international headlines. The team had analysed optical and infrared data from the Gaia Space Observatory, the 2-mast survey, and the WISE infrared telescope, scanning approximately 5 million stars within roughly 1,000 light-years of Earth. They were looking for something no one had ever systematically searched for at that scale: Dyson spheres. The concept goes back to the physicist Freeman Dyson in 1960. A sufficiently advanced civilization, he reasoned, would eventually need more energy than a single planet could provide. The logical next step would be to build a structure, or more likely a swarm of collectors, around its star to capture the star's entire energy output. Such a structure would not be invisible. The laws of thermodynamics guarantee it. It would absorb visible light from the star and re-emit that energy as infrared radiation. Waste heat. No matter how advanced the engineering, waste heat cannot be eliminated entirely. From a distance, a star surrounded by a Dyson sphere would look dimmer in visible light and brighter in mid-infrared. That is the signature you search for. The Hephaestus team developed a sophisticated pipeline using multiple filters, including a convolutional neural network, to identify stars with anomalous infrared excess that could not be easily explained by known astrophysical processes. Out of 5 million stars, the pipeline identified 7 candidates. 7 M-dwarf stars, small, cool, long-lived stars that are the most common type in the galaxy, showed excess mid-infrared emission consistent with what a partial Dyson sphere would produce. M-dwarfs are also the most energy-efficient targets for a megastructure project, because they burn for trillions of years, far longer than stars like our own. A civilization building for permanence would choose an M-dwarf the way you would build a house on stable ground rather than on a floodplain. The 7 candidates passed multiple scrutiny levels. The infrared excess was real. It was measured. The spectral profile did not match standard models of circumstellar dust or debris disks. Something unusual was going on around those 7 stars. The response was immediate. News outlets ran headlines about possible alien megastructures. Social media erupted. The paper accumulated hundreds of thousands of views within weeks. For a brief window, the scientific community allowed itself to consider the possibility that someone, somewhere, had built something around a star. To appreciate the scale of what a Dyson sphere would represent, consider this. Earth intercepts roughly 1/1000th of our Sun's total energy output. A complete Dyson sphere would capture all of it. That is an increase in available energy by a factor of 1 billion. The total output of every power plant on Earth combined is approximately 10 to the 13th watts. A Dyson sphere around a star like ours would produce roughly 3.8 times 10 to the 26 watts. The gap between our current civilization and a Dyson sphere civilization is 13 orders of magnitude. That is not a difference in degree. It is a difference in kind. Within months, the anomalies had a different explanation, and it was one that nobody involved in the original search had anticipated. Independent teams re-examined the 7 M-dwarf candidates using additional infrared and radio data. What they found was not alien megastructures, it was background contamination. The anomalous infrared excess was real, it just was not coming from the stars. It was coming from objects behind them, billions of light years further away. Dust-obscured galaxies, known in the astronomical literature as DOGs, and active galactic nuclei, the supermassive black holes at the centres of distant galaxies that emit enormous quantities of energy as they consume surrounding matter. These background sources happen to sit along the same line of sight as the M-dwarf candidates. Their infrared emissions blended with the starlight, creating the illusion that the stars themselves were producing excess heat. The resolution of the original survey was not fine enough to separate foreground stars from background galaxies at those angular scales. Once higher resolution data was applied, separating the faint background glow from the foreground starlight, the megastructure signatures vanished. The stars were ordinary. The infrared excess belonged to objects that had nothing to do with them. The paper demonstrating this contamination was published by Tongtian Ren, Michael Garrett, and Andrew Semien. They noted that with the known density of dust-obscured galaxies across the sky, roughly 9 per million square arcsecons, This level of contamination could statistically account for all 7 candidates from the original sample of 5 million stars. The math predicted the false positives. The universe had done it again. It had perfectly mimicked the signature of advanced technology using nothing but random cosmic geometry and hot dust. 5 million stars searched, 0 megastructures, 0 engineering at any scale. The galaxy looks precisely the way it would look if nobody had ever built anything in it. Meanwhile, one of Breakthrough Listen's own instruments had generated a false alarm that was even more dramatic. In 2020, the Parkes telescope in New South Wales detected a narrowband signal at 982.002 MHz. Narrowband signals are significant because natural astrophysical sources almost always produce broadband emissions, energy spread across a wide range of frequencies. A narrowband signal, concentrated at a single frequency, is one of the hallmarks of an engineered transmission, and this one appeared to come from the direction of Proxima Centauri, the nearest star to our own, just 4.24 light-years away, a star already known to host at least 2 planets, one of which sits in the habitable zone. The signal was designated BLC-1, Breakthrough Listen Candidate 1. It was the first signal the project had ever considered promising enough to earn a formal candidate designation. BLC-1 had characteristics that made seasoned scientists hold their breath. The signal drifted in frequency, which is what you would expect from a transmitter on a rotating planet. The Doppler shift caused by planetary rotation gradually changes the observed frequency. Earth-based interference does not typically drift the same way because both the transmitter and receiver are on the same rotating body. BLC-1's drift rate was consistent with what you would expect from a transmitter on a planet orbiting Proxima Centauri. The signal appeared only when the telescope was pointed at Proxima Centauri. When the dish moved to observe a reference direction away from the star, the signal vanished, and when it swung back to Proxima, the signal returned. This on-off pattern is the standard test for distinguishing celestial signals from local interference. BLC-1 passed it. For months, the Breakthrough Listen team worked in near secrecy. They reprocessed the data. They checked for known sources of interference. They cross-referenced with databases of terrestrial transmitters, satellites, aircraft, and ground-based electronics. They applied every filter in their pipeline. BLC-1 survived them all. Word eventually leaked to the press in late 2020. The story made international news. Scientists who had spent decades managing public expectations about SETI found themselves being asked a question they had always hoped to answer, but never expected to face directly. Is this it? It was not. In 2021, the Breakthrough Listen team published a thorough analysis in Nature Astronomy, showing that BLC-1 was almost certainly human-generated radio frequency interference. The key evidence was the discovery of structurally similar signals at nearby frequencies, signals that shared the same characteristics as BLC-1, but came from directions that had nothing to do with Proxima Centauri. The most likely source was electronics operating near the Parkes telescope itself. Intermodulation products, spurious signals created when multiple radio frequency sources interact and produce new signals at unexpected frequencies. The drift rate that had seemed so convincing turned out to be within the range producible by local interference under certain conditions. The on-off pattern could be explained by the telescope's side lobes, secondary sensitivity patterns outside the main beam that pick up local signals only at certain pointing angles. BLC-1 was electromagnetic noise from approximately 0 light-years away. The most exciting SETI candidate in decades had been generated by equipment sitting within a few hundred feet of the telescope's receiver. Imagine hearing a knock at your door in the middle of the night. You check through the glass. Nobody there. You open the door. Nobody. You step outside and hear the knock again. Then you realize that it's coming from the pipes inside your own wall. BLC-1 was the knock in the pipes the disappointment cut deeper than emotion. It was methodological. BLC-1 demonstrated that even the most sophisticated CT pipeline in the world, backed by $100 million in funding and decades of expertise, could be fooled by a signal originating within the telescope compound. If local interference can mimic every characteristic of an extraterrestrial transmission, the threshold for a confirmed detection becomes almost unreachable with a single instrument. Any credible claim would require simultaneous confirmation from multiple independent telescopes on different continents, observing the same signal at the same time and each independently ruling out every possible terrestrial source. And then there was the discovery that struck at the very foundation of how scientists planned to detect life at all: oxygen. For decades, free molecular oxygen in a planet's atmosphere was considered the gold standard biosignature. The reasoning was elegant. Oxygen is chemically reactive. It bonds with iron, carbon, silicon, and dozens of other elements readily. Leave a planet without something continuously replenishing the oxygen supply and it vanishes from the atmosphere within a few million years. On Earth, that something is photosynthesis. Plants and cyanobacteria split water molecules apart using sunlight, release oxygen as a byproduct, and keep the atmosphere stocked at roughly 21% concentration. If you point a telescope at a distant planet and detect free oxygen, something biological is probably maintaining it. Nothing else could. The James Webb Space Telescope was designed in part to do exactly this: analyze light filtering through exoplanet atmospheres and search for chemical fingerprints of gases that should not be there without biology producing them. Entire scientific careers were built around this assumption. Entire missions were justified by it. Then in July of 2024, a team of researchers published a paper in Nature, Geoscience, reporting that oxygen was being produced at the bottom of the Pacific Ocean, not by any living thing. The source was polymetallic nodules, lumps of metal ore sitting on the deep ocean floor in the Clarion-Clipperton Zone, at depths of roughly 4,000 meters, where no light from the surface reaches and photosynthesis is impossible. These nodules contain manganese, nickel, cobalt, copper, and other metals. The research team, led by Andrew Sweetman of the Scottish Association for Marine Science, discovered that the nodules generate small but measurable electrical voltages through natural electrochemical reactions. They recorded voltages of up to 0.95 volts on the surface of single nodules. When multiple nodules clustered together, the combined voltage increased, similar to batteries wired in series. That voltage is enough to split seawater molecules into hydrogen and oxygen through a process called electrolysis. The researchers dubbed it dark oxygen. Oxygen produced without any biology whatsoever, in total darkness, at the bottom of the sea. Franz Geiger, a professor of chemistry at Northwestern University and a co-author on the study, described the nodules as natural geobatteries. The researchers measured oxygen production rates that in some areas exceeded what the local microbial communities were consuming. The deep ocean floor was generating more oxygen than the life around it was using. If oxygen can be produced without life on Earth, in Earth's own ocean, it can be produced without life on a rocky planet orbiting a red dwarf star 40 light-years away. One of the most foundational assumptions in astrobiology, that atmospheric oxygen implies biological activity, had developed a significant crack. This did not render oxygen useless as a biosignature, but it meant that oxygen alone was no longer sufficient evidence. You would need additional confirming detections, other gases, chemical patterns that together pointed toward biology rather than geology or chemistry. And the James Webb Space Telescope was already struggling to get even single biosignature readings from exoplanet atmospheres. Adding the requirement for multiple, independent confirming signals from a single world made an already difficult measurement harder by at least an order of magnitude. the one planet where the telescope thought it had found a second biosignature, something beyond oxygen, something that on Earth is produced almost exclusively by living organisms, demonstrate exactly how fragile the detection framework had become. The planet is called K2-18b. It orbits a red dwarf star 124 light-years from Earth. In 2023, the James Webb Space Telescope analysed starlight passing through its atmosphere and reported what appeared to be dimethyl sulfide. On Earth, dimethyl sulfide is produced almost exclusively by marine phytoplankton. It is the molecule responsible for the distinctive smell of the seaside. Finding it on another planet would be remarkable because there is no known geological process that generates significant quantities of it without biology. The headlines were global: potential evidence of biological activity on an alien world. K2-18b became the most discussed exoplanet in the scientific community and in popular media almost overnight. Then the data was examined more carefully by independent teams. The dimethyl sulfide signal sat within the noise floor of the observation. The statistical confidence fell below what most scientists consider reliable for a formal discovery claim. Follow-up analyses using different atmospheric modelling approaches could not reproduce the result consistently. By early 2026, the scientific consensus had shifted. The detection was most likely an artifact of the data reduction process, a ghost in the numbers rather than a molecule in the sky. As of this investigation, no exoplanet has a confirmed atmospheric biosignature. Not K2-18b, not any of the 7 worlds orbiting TRAPPIST-1, not the planets catalogued by Kepler or the Transiting Exoplanet Survey satellite. 0. The pattern across the entire history of this search is now clear enough to state plainly. Pulsars in 1967 mimicked regular transmissions. The WOW signal in 1977 mimicked an intentional broadcast. BLC-1 in 2020 mimicked a signal from the nearest star. The Hephaestus candidates in 2024 mimicked partial Dyson spheres. K2-18b in 2023 mimicked a biological atmosphere. In every case, the universe offered a natural explanation that nobody had predicted in advance. The cosmos is not just silent, it is actively deceptive. It produces phenomena that look engineered, that pass our filters, that survive initial scrutiny, and then collapse into mundane physics when examined closely enough. And that raises a question that sits beneath all of SETI, beneath all of astrobiology, beneath every telescope and every pipeline and every algorithm. If the universe keeps generating perfect false positives that fool our best instruments, how confident can we be that we would recognize a genuine detection if one ever appeared? The honest answer, and it is an answer that working scientists are increasingly willing to give on the record, is not very confident at all. But the false positives and cosmic mirages are only one category of explanation for the silence. There is a darker one, and it does not come from the stars. It comes from the way human institutions have treated the search itself. In 2008, the Chinese science fiction writer Liu Cixin published the second novel in his 3-body trilogy. It was called The Dark Forest. The book proposed an answer to the Fermi paradox that was elegant in its logic and deeply disturbing in its implications. The universe, in Liu's telling, is full of civilizations. They are all silent, because revealing your location is functionally identical to committing suicide. The reasoning builds from 2 axioms. First, survival is the primary need of every civilization. Second, civilizations continuously grow and expand, but the total matter and energy in the universe does not. These 2 axioms create a problem. Resources are finite. Civilizations are potentially infinite. Any civilization that encounters another faces a choice: cooperate or destroy. But cooperation requires trust. Trust requires communication, and communication reveals your position. Here is where the logic becomes lethal. You cannot verify another civilization's intentions. They might be peaceful today and hostile in 1,000 years. They might be technologically inferior today and superior in a century. The only way to guarantee your own safety is to strike first, before the other civilization becomes a threat. And because every surviving civilization has independently arrived at the same conclusion, the result is a galaxy full of armed hunters standing motionless in the dark. Every sound, every signal, every electromagnetic footprint could attract a weapon. The rational strategy is to be absolutely silent and to eliminate anything that makes noise. Liu called this the Dark Forest. The hypothesis has a specific physical implication. A civilization following this logic would not build Dyson spheres, because Dyson spheres are visible across the galaxy. It would not broadcast radio signals, because radio signals reveal location. It would not expand aggressively, because expansion creates a detectable footprint. It would minimize its observable signature in every possible way. From the outside, it would look exactly like the silence we observe. Critics of the Dark Forest hypothesis point to several problems. It assumes a level of paranoia that may not be universal. It requires that every civilization independently arrives at the same conclusion, with no exceptions, because even one loud civilization would break the silence. It also assumes that destroying a distant civilization is easier than communicating with one, which is not obviously true given the distances involved. But the hypothesis has one property that makes it impossible to fully dismiss. It is entirely consistent with the observational data. The silence is exactly what a Dark Forest universe would look like. You cannot distinguish between a galaxy where nobody exists and a galaxy where everybody is hiding. Both produce the same measurement: 0. And this brings us to a real controversy that is not fictional, not theoretical, and not safely contained in a science fiction novel. It is happening right now, on Earth, and it involves the question of whether humanity should be shouting into that forest. In 1999, a Russian astronomer named Alexander Zaitsev did something that no international body had approved and no scientific consensus had endorsed. He used the Evpatory planetary radar facility in Crimea, a dish originally built for deep space communication with Soviet probes to transmit a high-powered Krasnoyarsk targeted message towards several nearby star systems. He called it Cosmic Call. The transmission was designed to be detectable by any civilization with a radio telescope comparable to our own. It contained mathematical and scientific information encoded in a format meant to be decipherable by any technologically capable species. Zaitsev did not consult the SETI community before transmitting. He did not seek approval from any government. He did not request international review. He did not need to, because there is no binding international protocol governing deliberate transmissions into space. None. There are guidelines. The International Academy of Astronautics has a set of recommendations for what is called METI, Messaging to Extraterrestrial Intelligence. But those recommendations are voluntary. No treaty, no law, no enforceable agreement prevents anyone with access to a sufficiently powerful transmitter from broadcasting a message into the cosmos right now, today, announcing humanity's existence and location to anything that might be listening. The reaction within the scientific community was immediate and bitter. David Brin, the physicist and science fiction author who had written extensively about the Fermi paradox and its implications, called the transmission reckless and potentially catastrophic. If the Dark Forest hypothesis had even a small probability of being correct, Brin argued, deliberately transmitting was the equivalent of lighting a bonfire in a forest full of predators. Brin resigned from SETI-affiliated committees in protest over what he viewed as a complete absence of governance over active messaging. Jill Tarter, who had spent 35 years directing SETI searches, including Project Phoenix, and who served as the real-world inspiration for the protagonist in the film Contact, found herself in the middle of the dispute. She supported the search for signals, but had serious reservations about transmitting them. Dan Wertheimer, a Berkeley astronomer and co-founder of SETI at Home, argued that any deliberate transmission should require global consensus. The idea that one individual or one country could make a decision with consequences for the entire species struck him as fundamentally unacceptable. Seth Shostak at the SETI Institute took the opposite position. His argument was practical. Earth's military radar systems have been leaking detectable signals into space for roughly 70 years. Anyone within 200 light years who has the technology to threaten us already knows we are here. Deliberately transmitting changes nothing. The metaphor he used is this: you are standing in a dark room and you have been coughing loudly for 7 decades. Someone suggests that maybe you should stop coughing, but you have been coughing the entire time. If something in the dark wanted to find you, it already has. The debate has never been resolved. It cannot be because the underlying question is unanswerable with current information. Is the universe dangerous, or is it not? And the dispute reveals something that most people assume about science, but is not true. People assume that the scientific community coordinates its relationship with the cosmos, that there are protocols and oversight and institutional controls over what humanity says to the stars. There are not. The METI controversy proved that any individual with the right equipment can speak for the entire species without asking permission from anyone. The implications of this gap in governance go beyond the specific transmissions that have already been sent. As radar technology improves, and as more nations develop high-powered directional transmitters for defense and space tracking purposes, the number of people and institutions capable of broadcasting detectable signals into space will grow. China's FAST telescope, for example, could theoretically be used as a transmitter. Russia's Evpatoria dish has already been used for this purpose. The Deep Space Network facilities operated by NASA, ESA, and other space agencies routinely send commands to distant spacecraft at power levels that would be detectable across interstellar distances if someone happened to be listening in the right direction. There is no international protocol that governs any of this. The Outer Space Treaty of 1967 addresses the use of nuclear weapons in space and the sovereignty claims over celestial bodies. It says nothing about broadcasting messages. The Committee on the Peaceful Uses of Outer Space, which operates under the United Nations, has not produced binding regulations on METI. The International Telecommunication Union regulates the allocation of radio frequencies on Earth, but has no jurisdiction over transmissions aimed at other star systems. The result is a situation where the most consequential communication in the history of the species, announcing our existence to the universe, is subject to fewer regulations than the operation of a commercial radio station. Any nation, any institution, any sufficiently wealthy individual can broadcast at will, and we would not know if something responded until the reply arrived, travelling at the speed of light, decades or centuries after the original message was sent. The time delay is its own form of insulation. If a reply came from a star 50 light years away, it would arrive 100 years after the original broadcast, long after the person who sent it had died. The consequences of the decision would fall entirely on people who were never consulted, and whether or not anyone is listening on the other end. The tools we have built to find out keep getting destroyed. On December 1st, 2020, the 900-ton receiver platform of the Arecibo Observatory broke free from its cables and crashed through the 305-metre radio dish below. The collapse was not sudden. Engineers had been warning about cable degradation for months. 2 cables had already failed, one in August and one in November. Each failure had added stress to the remaining cables, creating a cascading risk that made the entire structure increasingly unstable. The National Science Foundation made the decision not to attempt repairs because sending workers onto the structure to replace cables posed an unacceptable risk to human life. There was no safe way to fix it. When the final cables gave way, the platform fell from a height of roughly 450 feet, punching through the dish and destroying the structure that had been the largest single-aperture radio telescope in the world for 53 years. The NSF chose not to rebuild. The estimated cost of a new facility was significant, but it was not beyond the reach of a nation that spends hundreds of billions of dollars annually on defense. The decision reflected priorities, not capabilities. Arecibo was allowed to die because the political and institutional will to save it did not exist. The loss was not merely symbolic. Arecibo had capabilities that no other single instrument could replicate at the time. It could function both as a receiver and as a powerful radar transmitter, allowing it to bounce signals off asteroids, planets and moons and read the returning echoes. This dual capability made it essential for mapping near-Earth objects, the asteroids whose orbits bring them close enough to Earth to pose potential collision hazards. Without Arecibo, humanity lost a significant portion of its ability to track the very objects that could end civilization entirely. The telescope that searched for intelligent life in the cosmos also served as an early warning system for unintelligent rocks that could wipe us out. Both functions were lost simultaneously. Arecibo had been used for SETI at home, Project Phoenix radar mapping of near-Earth asteroids, pulsar research, atmospheric studies, and dozens of other scientific programs. It transmitted the famous Arecibo message in 1974, a binary encoded transmission aimed at the globular cluster M13, designed by Frank Drake and Carl Sagan as a demonstration that humanity could send a message into the cosmos. It had detected the first binary pulsar, a discovery that confirmed the existence of gravitational waves decades before they were directly measured by LIGO, and that won the 1993 Nobel Prize in Physics. It had contributed to the discovery of the first exoplanets orbiting a pulsar, the first evidence that planets existed beyond our solar system. It was one of the most scientifically productive instruments ever built, and when it fell, the scientific community mourned it the way you mourn a colleague who died of neglect. It was gone, and nobody rebuilt it, but Arecibo was not the first loss. The Big Ear telescope in Ohio, the instrument that captured the WOW signal in 1977, had been demolished 2 decades earlier, so the land could be turned into a golf course. The most promising candidate signal in the history of SETI, and the telescope that found it, was paved over for a driving range. The Allen Telescope Array, a field of 42 dishes in Northern California designed specifically and exclusively for SETI, was built as a joint project between the SETI Institute and the University of California at Berkeley. In 2011, the array was placed into hibernation. The reason was money. The SETI Institute could not afford $1.5 million per year to keep it running. To put that in perspective, a single F-35 fighter jet costs approximately $80 million. The annual operating budget of the only telescope array, built specifically to search for extraterrestrial intelligence, was roughly equal to what the United States military spends in less than 2 minutes. The array was later reactivated with private funding, but the episode illustrated a pattern that is repeated throughout the history of the search. The federal funding history is even more pointed. NASA's first dedicated SETI program, the High Resolution Microwave Survey, launched in October 1992 with a $12 million annual budget. It combined a targeted search using Arecibo with an all-sky survey using the Goldstone Deep Space Communications Complex. It was a serious, well-designed scientific program with the backing of the space agency. It lasted 1 year. The program had a predecessor that died even faster. In the early 1980s, NASA had proposed a smaller SETI initiative. Senator William Proxmire of Wisconsin gave it his Golden Fleece Award, a prize he invented for what he considered the most wasteful examples of government spending. The award was public, embarrassing, and effective. The program was killed. Carl Sagan, who was already one of the most famous scientists in the world, personally lobbied Proxmire and eventually convinced him to reverse his position. The program was briefly revived. Then in 1993, Senator Richard Bryan of Nevada permanently defunded the High-Resolution Microwave Survey. The program had been running for approximately 12 months, $12 million per year. That is roughly the cost of building 600 feet of interstate highway. The search for an answer to one of the most fundamental questions humanity has ever asked, are we alone in the universe, was killed over an amount of money that would not cover a single highway on-ramp. Since 1993, every major SETI effort has been privately funded. The entire field depends on the generosity of individual donors and the occasional billionaire who decides that the question matters enough to write a check. Breakthrough. LISTEN exists because Yuri Milner committed $100 million. The Allen Telescope Array exists because Paul Allen donated money to build it. The cosmic system on the VLA exists because private organizations funded the hardware. The pattern is worth stating plainly. The telescope that caught the best signal was demolished for real estate. The telescope array built specifically for the search was shut down over the cost of a rounding error in the defense budget. The federal program was killed for politics after running for 12 months. The largest radio dish in the Western Hemisphere was allowed to collapse and was never rebuilt. If you were designing a civilization that would never detect an extraterrestrial signal, this is approximately how you would do it. In 2015, when Yuri Milner stood on that stage in London alongside Stephen Hawking and announced Breakthrough Listen, it represented a rescue operation as much as a scientific initiative. $100 million over 10 years, dedicated to the most thorough search ever attempted. The project gained access to Green Bank, Parkes, Meerkat, and the automated Planet Finder at Lick Observatory. Its instruments could detect a transmitter equivalent to a small nuclear power plant from nearby star systems. If anyone in the local stellar neighbourhood was broadcasting, Breakthrough Listen would have found them. The search strategy was straightforward. Point the best instruments at the most promising targets and listen at every frequency simultaneously. The data volumes were staggering, 2 petabytes and counting. The sensitivity surpassed anything previously achieved. In November of 2025, the project deployed an artificial intelligence system running on NVIDIA's Holoscan platform at the Allen Telescope Array. The system processes radio telescope data 600 times faster than conventional methods. A delta set that would have taken a human team years to analyze can now be filtered in days. The combined effect of all of these programs, public and private, past and present, is the most comprehensive electromagnetic survey of the cosmos ever conducted by any species as far as we know. Billions of dollars in cumulative investment, thousands of scientists, dozens of instruments on every continent, frequency coverage spanning from low megahertz to optical wavelengths, 65 years of accumulated observation time. The result? 0. Now. The investigations we have followed so far have dealt with the science of the silence, the telescopes, the signals, the filters, the false alarms. But there is one more dimension to this story that rarely gets the attention it deserves, and it has to do with what happens when you take the silence seriously, not as a puzzle to be solved, but as information to be interpreted. For decades, there was a standard defense against drawing conclusions from the silence. Jill Tarter, more than anyone else, gave this defense its most memorable expression. Imagine you want to know if there are fish in the ocean. You walk to the shore, scoop up a single glass of water, look inside and find nothing. Would you conclude the ocean has no fish? That was the argument. All of SETI's searching, every dish pointed at every star, every frequency scanned, every algorithm run, amounted to a glass of water scooped from a cosmic ocean. The galaxy is enormous. Our instruments are limited. Less than 1% of the sky has been searched at the frequencies and sensitivities that matter. The hot tub argument, as it came to be known, sounded reasonable. It sounded humble. It acknowledged the limits of human technology in the face of a universe that is almost incomprehensibly vast. And for a long time, it was enough to keep the question open without forcing uncomfortable answers. But the hot tub argument has stopped working. Not because someone came up with a clever rebuttal, because the data has simply outgrown it. SETI at home processed 12 billion candidate signals over 21 years. Breakthrough. LISTEN scanned approximately 1 million nearby stars. COSMIC covered 950,000 unique fields in under a year. The Murchison Wide Field Array surveyed 2,800 entire galaxies. The Allen Telescope Array stared at TRAPPIST-1 for 28 continuous hours. Breakthrough. LISTEN observed an interstellar object with telescopes on 3 continents, recording 74 million narrowband hits. Each of these programs used different instruments, different frequencies, different analysis pipelines, different parts of the sky. The combined result was always the same number. Statistical models, built on 6 decades of accumulated null results, now estimate that the number of detectable technological civilizations active in the Milky Way at any given time is fewer than 1 to 5 per century. That is not a glass of water from the ocean. That is a measurement of the ocean itself. The sampling has been conducted at enough points, with enough variety, over enough time that the absence of fish is telling you something real about the water. The shift is subtle, but it changes everything. For 60 years the silence was treated as a gap in knowledge, a blank space waiting to be filled by better instruments or more patience. The new interpretation treats the silence as data in its own right. The way a blood test that comes back negative is still a medical result. The way an X-ray that shows no fracture is still diagnostic information. 0 is not nothing. 0 is a finding, and that finding lands with weight, because it closes off the most comfortable exit. You can no longer say we just have not looked hard enough. Not anymore. Not after 12 billion processed candidates and 74 million narrowband hits from an interstellar visitor, all collapsing to the same number. The silence, then, is information. And once you accept that, the investigation shifts from asking why we have not found anything yet, to asking what 0 actually means for a species that is still inside its own detectable window. Start with what the evidence has established. 65 years of organised searching, from Project Ozma to the Commensal open source multi-mode interferometer cluster. 12 billion candidates from SETI at home. 74 million narrowband hits from an interstellar visitor. Every candidate resolved to noise, interference, or a natural phenomenon nobody predicted. Every promising detection, pulsars in 1967, the WOW signal in 1977, BLC-1 in 2020, Dyson Sphere candidates in 2024, dimethyl sulfide on K2-18b in 2023, either debunked or unconfirmed. The pattern is unbroken. Every measurable variable in the Drake equation moved in a more optimistic direction since 1961. More stars have planets. Habitable zones are more common. Life starts faster than predicted. The count of Earth-sized habitable zone worlds went from an educated guess to 40 billion in our galaxy alone. Each revision should have made silence less probable. Instead, each revision made the silence more statistically significant, because the expected number kept climbing while the observed number stayed fixed. The gap between prediction and observation grew wider with every discovery, not narrower. The filters stack. At every stage of the journey from chemistry to interstellar communication, something narrows the funnel. Intelligence may require a very specific geological history. Continuous plate tectonics for hundreds of millions of years, a particular ratio of land to ocean, a stable climate maintained by carbon cycling over timescales that most planets do not provide. The fraction of life-bearing planets that develop technology-capable intelligence may be extremely small, measured in fractions of a percent rather than the near certainty that early estimates assumed. But even if intelligence arises, the civilization that follows faces its own gauntlet. Artificial intelligence, within approximately 2 centuries of the first radio transmission, may either transform or terminate the civilization that created it. The demographic mathematics of prosperity and reproductive choice may erode the population base required to sustain a technological society within 500 to 1,000 years. The detection window during which any civilization produces electromagnetic signals strong enough to cross interstellar distances may be as narrow as 100 years. 100 years against 13.6 billion years of cosmic history. A single water droplet falling into a lake. The instruments keep getting destroyed, defunded, or demolished. The biosignatures we trusted have proven less reliable than believed. The international governance structures that should exist to manage humanity's relationship with the cosmos do not exist, and the most comprehensive search ever conducted, using the most powerful instruments ever built, with the most sophisticated analysis pipelines ever designed, continues to return the same number. It has returned every year since 1960. 0. That is the state of the investigation. What follows is not conclusion, it is interpretation. And there are several ways to interpret the data, each of which leads to a very different picture of our place in the universe. The first interpretation is the simplest. We are early. The universe is 13.6 billion years old, but the conditions necessary for complex life may not have existed for most of that time. The earliest generations of stars were made almost entirely of hydrogen and helium. They had to live, die, and explode as supernovae to seed the interstellar medium with heavier elements like carbon, oxygen, iron, and silicon, the building blocks of rocky planets and organic chemistry. It took multiple generations of stellar recycling before the galaxy contained enough heavy elements to build worlds like Earth. Some estimates suggest that Earth-like planets with sufficient chemical complexity to support life could not have formed in significant numbers until roughly 5 to 8 billion years after the Big Bang. If that is correct, then the window during which intelligence could have arisen in the Milky Way is not 13.6 billion years. It might be closer to 5 or 6 billion years. Earth is 4.5 billion years old. It took all of that time to produce a species capable of radio communication. If we are near the front of that timeline rather than in the middle or at the tail end, the silence might simply reflect the fact that nobody else has had enough time yet. We might be among the first. Not the only ones, but the earliest. The galaxy might be on the verge of filling up with civilizations in the next billion years. We just arrived too soon to see any of them. This is the optimistic interpretation. It places no filter ahead of us. It requires no catastrophe, no extinction mechanism, no dark forest. It simply notes that the universe is young and the timeline for producing technological civilizations is long. The silence under this reading is not a graveyard. It is an empty nursery. The other children have not been born yet. The second interpretation is less comfortable. Civilizations arise, they broadcast for a geological instant and they go quiet. Not because they die, because efficiency or transformation or a simple loss of interest in omnidirectional communication removes them from the electromagnetic spectrum. Earth itself is the evidence for this. We are already transitioning from leaky broadcast to directed, encrypted, fiber-based communication. Within a few decades, our unintentional radio emissions may drop below the detection threshold of any realistic alien telescope. A civilization 1,000 years ahead of us might communicate through means that are entirely invisible to our instruments. Tight beam lasers, quantum encrypted channels, neutrino-based transmissions, technologies that do not scatter, do not leak, and leave no detectable residue for anyone not standing directly in the beam. Under this interpretation, the galaxy might be full of civilizations that are simply invisible to radio telescopes. They graduated from the loud phase into the quiet phase, the same way every human society has transitioned from shouting in the town square to whispering through fiber optic cables. The silence is not absence. It is technological maturity. The problem with this interpretation is that it has to be universal. Every single civilization that has ever existed in the Milky Way must have followed the same path. Not most. Not 99%. All of them. Because if even one civilization in the galaxy's history had decided to remain loud, to build megastructures, to expand aggressively across the stars, to leave a mark, we would see evidence of it. The Hephaestus search covered 5 million stars. The Murchison Wide Field Array surveyed 2,800 galaxies. Nothing at any scale in any direction shows evidence of deliberate engineering. For the quiet hypothesis to fully explain the silence, there can be no exceptions. That is a very strong requirement, and it is difficult to justify the claim that every civilization that has ever existed, across billions of years and billions of galaxies, independently chose to go silent without exception. The third interpretation is the one proposed by Robin Hansen's Grabby Aliens model. If even a small fraction of technological civilizations decide to expand outward from their home systems, travelling at even a modest fraction of the speed of light, they should be visibly reshaping the Milky Way by now. A single civilization expanding at 1% of light speed, roughly 6.7 million miles per hour, would fill the galaxy in 10 to 100 million years. The galaxy has had enough time for this to happen thousands of times over. Hansen's mathematical model calculates that for multiple civilizations to coexist in the same galaxy without encountering each other, they would each need average lifespans exceeding 280,000 years. For context, anatomically modern humans have existed for roughly 300,000 years total. We have possessed technology capable of interstellar travel for exactly 0 of those years. If Garrett's model gives civilizations 200 years after developing AI, and if the demographic data suggests a 500 to 1,000 year window before population decline compromises technological capacity, neither comes remotely close to the 250,000 year threshold that expansion requires. The conclusion is blunt. Civilizations do not expand because they do not last long enough to begin expanding. They appear, broadcast briefly, and vanish. The galaxy remains precisely as empty as it looks. The fourth interpretation is the one that most working scientists refuse to take seriously, but none can formally rule out. In 2001, the science fiction writer Stephen Baxter published a thought experiment he called the Planetarium Hypothesis. The idea is straightforward in construction and disturbing in its implications. If a civilization existed that was sufficiently advanced, thousands or millions of years beyond our current level, it could enclose our solar system in a projected simulation, a perfect replica of an empty universe displayed inward from the boundary, so that every telescope, every satellite, every instrument humanity builds shows us exactly what the builders want us to see. We would observe an empty cosmos, because the cosmos we are permitted to observe has been constructed for our observation. It is related to the older zoo hypothesis, proposed by the physicist John Ball in 1973. Ball suggested that advanced civilizations might deliberately avoid contact with primitive species, the way a wildlife preserve keeps human visitors away from animals being studied. The animals do not know they are being observed. They do not know the fence around the reserve exists. They live in what appears to be a natural environment, unaware that their environment has been curated. The planetarium hypothesis takes Ball's idea one step further. The advanced civilization does not merely avoid us, it actively constructs the reality we observe. The fence is not around us. Everything we see is the fence. Scientifically, the hypothesis has a fundamental problem. It is unfalsifiable. There is no observation you could make, no experiment you could design, no data you could collect that would prove or disprove that you are inside a simulation, because any evidence of the simulation could itself be part of the simulation. That makes it bad science by any standard definition. It sits outside the reach of the scientific method entirely, but it is logically consistent with everything we observe, and it exposes something uncomfortable about this entire investigation. Every explanation for the silence, the great filter, the dark forest, the zoo, the quiet hypothesis, the temporal coincidence argument, rests on the assumption that we are seeing the actual universe as it actually exists. If that assumption is wrong, every conclusion built on top of it collapses. Now, all of these interpretations are speculative. They are hypotheses. They are thought experiments. But there is one piece of hard evidence that cuts through the speculation because it is not a hypothesis. It is a measurement taken from Earth itself, and it makes the question harder, not easier. Life appeared on this planet almost immediately. The Earth formed approximately 4.54 billion years ago. The surface was molten. Asteroids bombarded it relentlessly. Temperatures were incompatible with any known biology. Yet within 300 to 400 million years of the planet cooling enough to sustain liquid water, life was present. The last universal common ancestor, Luca, existed approximately 4.2 billion years ago. If you compress Earth's entire history into a single calendar year, life appears before the end of February. Dinosaurs do not appear until December. Humans arrive in the final minutes of December 31st. That speed is staggering, and it has gotten harder to dismiss as a fluke. If abiogenesis were a 1 in a trillion accident, you would expect it to take billions of years even under favourable conditions. It did not. It happened fast. And the recent research into the co-evolution of amino acids and RNA nucleotides, showing that the building blocks of life likely emerge simultaneously through cooperative chemistry, rather than through a sequence of improbable individual events, makes the origin of life look more like a broad chemical highway than a narrow tightrope. If life is that easy to start, and the galaxy contains 40 billion potentially habitable worlds, then microbial life is probably common. It may be as ordinary as rocks. The bottleneck is not life itself. Earth spent more than 3 billion years populated exclusively by single-celled organisms before multicellular life appeared. That is not a brief delay. That is most of the planet's history. The bottleneck may not even be intelligence entirely, though the estimated fraction of life-bearing planets that develop intelligent species, perhaps between 3 in 100,000 and 2 in 1,000, makes that filter formidable. Intelligence appeared on Earth, so we know it is possible. But it took 4.5 billion years, and it required a chain of evolutionary and geological conditions that may be uncommon. The real bottleneck, the one that the data increasingly points toward, may be the final step. Building a technological civilization that persists, building something that does not collapse or fade or go quiet before anyone in the neighborhood has a chance to notice it exists. That word, building, keeps surfacing in this investigation. The difficulty is not starting life. The difficulty is sustaining complexity. And this is where the investigation arrives, at a question it cannot answer, but cannot avoid. In the mountains of Guizhou province, in southwestern China, a natural limestone depression holds the largest single-dish radio telescope ever constructed. The 500-metre aperture spherical telescope, known by the acronym FAST, stretches 500 metres from edge to edge. If you placed it in the middle of a major city, it would cover the distance of several long blocks in every direction. FAST replaced the Arecibo Observatory as the world's most sensitive radio ear after Arecibo collapsed in December of 2020. Its 4,400 individual aluminum panels adjust in real time, giving it both enormous collecting area and the ability to track targets precisely as they move across the sky. FAST has been conducting SETI observations as part of its scientific program. China's national strategy for the telescope explicitly lists detecting interstellar communication signals as one of its objectives. The instrument represents the most powerful single-dish radio receiver currently operating anywhere on Earth. As of early 2026, FAST has not reported the detection of any confirmed extraterrestrial signal. Meanwhile, machine learning algorithms developed for breakthrough listen process radio telescope data 600 times faster than conventional methods, as demonstrated in the deployment at the Allen Telescope Array using NVIDIA's Holoscan platform. A dataset that would have taken a human team years to analyse can now be filtered in days. The volume of sky being systematically searched per unit of time is growing exponentially, compared to even 5 years ago. The Allen Telescope Array itself is being upgraded to cover frequencies up to 18 GHz. New commensal systems instruments that piggyback on existing telescopes the way Cosmic rides the VLA, are being installed on radio telescopes across 4 continents. The search has never been faster, it has never been broader, it has never been more sensitive. And the number at the end of every pipeline remains the same number it has been since Frank Drake pointed an 85-foot dish at 2 stars and heard nothing in 1960. There is a version of this story where FASTA picks up something genuine. There is a version where the next breakthrough listen, data release, contains an anomaly that survives every verification test. Those versions are not impossible. 65 years of searching is a long time by human standards. By cosmic standards, it is barely a heartbeat. The argument that we have not looked long enough still carries weight, even if the hot tub analogy no longer captures the full picture. But 65 years of consistent precedent does make a prediction about the next result. And the prediction is 0. That prediction forces the question this investigation has been building towards since its opening lines. Not where is everybody? Because Fermi asked that 76 years ago, and the question has been asked, and re-asked, and reformulated by every generation of scientists since. The question now is what the answer means for a species that is still broadcasting, still building, still inside whatever window exists between developing technology and whatever happens next. Earth has been broadcasting for roughly 100 years. The first radio signals powerful enough to escape the atmosphere date to the early 1920s. Military radar from the middle of the 20th century, peaking at around 10 to the 14th watts directional, is the loudest thing this planet has ever produced. Those signals expand outward at the speed of light in a sphere currently about 100 light years in radius, containing roughly 15,000 stars. A civilization with a Green Bank-class telescope aimed at our star during the right century could detect us. But Earth is already getting quieter. The shift from broadcast television to streaming, from analog radio to digital compression, from omnidirectional radar to phased arrays, from open signals to encryption that is indistinguishable from random noise. All of it shrinks the electromagnetic footprint year by year. A civilization 1,000 years ahead of us might communicate through methods that generate no detectable leakage at all. Their signals would vanish into the background. They would be invisible. If Garrett's model is accurate, the window between a civilization's first radio transmission and the point at which artificial intelligence either transforms or terminates, that civilization is roughly 200 years. Earth is 127 years into that window, measuring from Marconi's 1895 demonstration. If the demographic data is the more relevant timeline, the window stretches to perhaps 500 or 1,000 years. Take the generous estimate, 1,000 years of detectability in a galaxy 13.6 billion years old. There is a ratio of roughly 1 to 13.6 million. For another civilization to notice us, it would need to exist at the same time, within detection range with instruments pointed in our direction, tuned to the right frequency, during our window. We would need the same from them. The probability of 2 civilizations overlapping in both space and time is not 0, but it is small enough to explain the silence entirely on its own, without invoking any great filter, any dark forest, any existential catastrophe. 2 fireflies blinking in a forest the size of a continent. Each flash lasts a fraction of a second. Each firefly is real. They miss each other by 100,000 years and never know the other existed. In July of 2025, the Allen Telescope Array tracked the 3rd confirmed interstellar object through our solar system. 7¼ hours of continuous listening, 74 million narrowband signals recorded, 211 candidates after automated filtering, every single one traced back to Earth, somewhere around another star. Right now, an instrument may have scanned our system last week and found the same thing. Nothing. Not because we are not here, but because our signals have not reached them yet, or because their window closed before ours opened, or because they are listening on a frequency we are not using, or because they already graduated to a communications technology that is invisible to radio telescopes. The silence does not prove we are alone. That is an important distinction, and it is worth repeating. The silence does not prove we are alone, but it is entirely consistent with a universe where the window of detectability is small, where the distances between stars are immense, and where 13.6 billion years is simply not enough time for brief flashes of technological activity to overlap across a galaxy 100,000 light-years wide. The most common outcome may be the simplest one. Civilizations arise, develop technology, broadcast for a geological instant and go quiet. The galaxy could be full of ruins. It could be full of species that are silent by physics rather than by choice. It could contain thousands of civilizations that existed millions of years apart and never coincided. Any of these possibilities produces the same observable result: 0. FAST is still listening in Guyot. The James Webb Space Telescope is still analysing exoplanet atmospheres, searching for the chemical fingerprints that might one day constitute a confirmed biosignature. Breakthrough. LISTEN is processing data 600 times faster than it could 5 years ago. The Allen Telescope array is being upgraded. Cosmic is watching everything the VLA watches. Newcomb and Sewell systems are coming online. The search is accelerating, the tools are improving. The question Enrico Fermi asked over lunch in 1950, the question that silenced a table of the smartest people in the world, has not been answered. And the window, whatever its true length, is still open. Something about the journey from microbe to interstellar civilization is so difficult, so improbable, or so brief that in 13.6 billion years it has either never been completed or never lasted long enough to leave a visible trace. That is not philosophy. That is not speculation. That is what the accumulated data of 65 years of searching, involving thousands of scientists, hundreds of millions of dollars, and the most sensitive instruments humanity has ever built, actually says. There is a way to make that statement tangible. Consider the timeline of a single human life, compressed to represent the history of the Milky Way. If the galaxy's 13.6 billion years were represented by an 80-year human lifespan, then 1 million years would be about 2 days. The entire history of anatomically modern humans, roughly 300,000 years, would fit into about 90 minutes. The age of radio communication on Earth, a little over a century, would be less than half a second. A blink. The entire span of a humanity's capacity to be detected from across the stars is a single involuntary blink in an 80-year life. The probability that another civilization happened to blink during the same half second, within earshot, is what SETI is trying to capture. And yet the search matters. It matters for reasons that go beyond the probability of success in any given decade. Because the search is, fundamentally, an act of self-definition. It is the only experiment that asks not just how the universe works, but whether the universe contains anyone else who has asked the same question. The answer, whatever it turns out to be, changes what it means to be human. If we find a signal, everything changes. The discovery of even a single, confirmed extraterrestrial transmission would be the most consequential event in the history of our species. It would mean that the Great Filter, whatever it is, can be survived, that intelligence can persist long enough to communicate across the stars, that we are not necessarily doomed by the same mechanisms that silenced everyone else. The confirmation that a single other civilization exists anywhere in the observable universe would rewrite philosophy, religion, biology, and politics overnight. If we never find a signal, that too is an answer. It means that what we have here on this planet may be genuinely unique. Not unique in the trivial sense that every snowflake is unique, but unique in the profound sense that in a cosmos of 2 trillion galaxies and a number of planets so large that the human mind cannot meaningfully comprehend it, the phenomenon of consciousness, of curiosity, of the desire to know whether anyone else is out there, may have occurred exactly once. That possibility is equally transformative, because if this planet is the only place in the observable universe where anyone has ever looked up at the stars and wondered, then what happens here matters in a way that no other framing of human significance has ever captured. We are not simply one species on one planet in one galaxy. We are the galaxy's only chance to know itself. We are the universe's only eye turned inward. And if we go quiet or go extinct or simply stop asking, the question dies with us, and the cosmos returns to being a machine that runs beautifully, but has nobody watching. The telescope at FAST is 500 meters across. It sits in a limestone depression in a mountainous region of southern China, surrounded by terrain so rugged that the radio interference from human activity is naturally low. The location was chosen specifically for its electromagnetic quietness. The Chinese government relocated thousands of residents from nearby villages to reduce radio contamination. When the FAST listens, it is the most sensitive ear on Earth, capable of detecting signals fainter than anything that came before it. Its collecting area is roughly 30% larger than Arecibo's was, and its receivers cover frequencies from 70 MHz to 3 GHz. It is, in a very literal sense, the pinnacle of human listening technology. The most refined instrument our species has ever built for the sole purpose of hearing something that might be speaking across the void. FAST began science operations in January 2020, less than a year before Arecibo collapsed. In a strange twist of timing, the world's most powerful radio telescope came online just months before the second most powerful one was destroyed. The transition was not planned, it was accidental, but the result was that the centre of gravity for radio astronomy, and for any future sea-tide discovery, shifted from the Caribbean to southern China. The telescope's SETI program is integrated into its broader scientific mission. China has explicitly listed the detection of interstellar communication signals among FAST scientific objectives. The instrument has already made significant contributions to pulsar astronomy, discovering hundreds of new pulsars since it became operational. It has detected faint hydrogen emissions from distant galaxies. It has contributed to the study of fast radio bursts, those mysterious millisecond duration flashes of radio energy that originate from across the universe and whose cause is still debated. In 2022, FAST detected what initially appeared to be narrowband signals of potential interest. After analysis, they were attributed to terrestrial radio interference, continuing the unbroken pattern of every promising detection resolving to a mundane explanation. And it hears the universe talking to itself, pulsars spinning, hydrogen clouds drifting, fast radio bursts flashing and vanishing. The cosmos is noisy with natural processes. It is alive with physics. What it is not, so far, is alive with anyone else's technology. There is a loneliness in that fact that is easy to overlook if you stay focused on the science, but the science ultimately is a proxy for the emotional weight of the question. Are we alone? We ask it as scientists with instruments and equations and statistical models, but we feel it as humans, and the feeling does not get easier as the data accumulates, because every null result adds another gram of weight to the possibility that the answer is yes. The searches will continue. They should. The James Webb Space Telescope has observation time allocated for exoplanet atmospheric characterization across multiple cycles. The next generation of ground-based telescopes, including the extremely large telescope under construction in Chile, will have the capacity to directly image exoplanets and analyse their atmospheres with spectral resolution far beyond what Webb can achieve. Breakthrough. LISTEN's mandate runs through the mid-2020s and shows no sign of stopping. Cosmic will continue to ride the VLA for years to come. The Square Kilometre Array, a next-generation radio telescope being built across sites in South Africa and Australia, will begin science operations later this decade and will have sensitivity that dwarfs everything currently operational. The tools are getting better, the sky coverage is expanding, the analysis is accelerating, and the probability that the next result will be different from the last 65 years of results is non-zero. That is the honest scientific statement. It is non-zero. The universe may yet yield a signal that survives every filter, passes every test, and forces us to confront the fact that we are not alone. But but the silence has persisted long enough, and across enough instruments and enough frequencies and enough targets that it can no longer be treated as merely the absence of a discovery. It is becoming year by year and petabyte by petabyte a discovery in its own right. The universe had time, it had space, it had the chemistry. On at least one planet, life started almost immediately and eventually produced a species that built radio telescopes and asked, where is everybody? The answer so far is silence, but the instruments are still running, the dishes are still turning, the data is still flowing, and somewhere out there, 40 billion worlds are doing whatever they're doing in the light of their own stars, in the quiet of their own skies, and we do not yet know if any of them are listening. The silence is not empty, it just is not talking to us yet.